Welcome to this explainer. Now, if you've ever had the privilege of standing under a clear, dark sky and watching the northern or southern lights dance overhead, well, you know it's an almost ethereal experience. Just these beautiful, silent ribbons of green, pink, and red rippling across the stars. But here's the crazy thing. What looks incredibly peaceful from down here on Earth is actually the visible fingerprint of something incredibly violent happening up in space. We are literally looking at the final act of a chaotic, supersonic plasma physics display that starts millions of miles away. So today we're going to unpack exactly what the aurora is, how it works, and why it is so much more than just a pretty light show. Okay, let's dive into this. Here's our roadmap for today. We'll start with 1, ancient myths to modern science. Then look at 2, the Sun-Earth connection. Explore 3, painting the night sky. Discuss 4, the space weather threat. And finally end with 5, beyond our home planet.
All right, part 1, ancient myths to modern science. You know, since the days of ancient cave paintings dating back 30,000 years, humans have been trying to figure out these lights. Early philosophers wrestled really hard with trying to logically explain what they were seeing. Take the Roman philosopher Seneca, for example. He described the aurora as chasms in the sky through which fire was visible. And honestly, for someone living 2,000 years ago, describing a glowing plasma emission as fire in the sky is a surprisingly accurate metaphor. It actually wasn't until 1619 that astronomer Galileo Galilei officially coined the term we use today, Aurora Borealis, which combines the Roman goddess of the dawn with the Greek god of the north wind. But while Galileo gave it a name, he still didn't know the cause. For that, we actually have to look away from Earth.
Moving on to part 2, the Sun-Earth connection. Every single auroral display you see on Earth actually originates 150 million kilometers away, with supersonic solar wind blowing from the sun. And sometimes, the sun violently burps out these massive bubbles of magnetized plasma called coronal mass ejections. But here is an absolutely crucial and widely misunderstood point about the aurora. The light you see? It isn't directly produced by solar particles raining down on us from the sun. Instead, it relies on a process called magnetic reconnection. See, when the solar wind carries a magnetic field that points south, which is opposite to Earth's northward magnetic field, the two fields merge. This essentially opens a massive magnetic door, transferring immense solar energy right into Earth's protective magnetic bubble, the magnetosphere. This energy stretches Earth's magnetic tail out like a giant rubber band until it snaps back, accelerating Earth's own trapped electrons down toward the poles.
Let's move to Omilia and see how this builds by tracking the micronarrative of just one single energetic particle. Step 1. The sun releases a burst of solar wind. Step 2. A few days later, that plasma hits the edge of Earth's magnetosphere. Step 3. Thanks to that magnetic reconnection we just talked about, solar energy gets stored in Earth's magnetic tail, eventually snapping and accelerating an electron down Earth's magnetic field lines at incredible speeds. Which brings us to Step 4. That energized electron crashes violently into the gases of our upper atmosphere.
And that brings us to part 3, painting the night sky.
Now, what's really interesting about this slide is that this crash is where the magic happens. When those energized magnetospheric electrons slam into Earth's upper atmosphere, they excite oxygen and nitrogen atoms. To settle back to a normal, stable state, those atoms release tiny packets of light called photons. What's truly fascinating here is that the colors you see, they aren't random at all. An aurora photograph is actually a precise, remotely sensed map of our atmospheric chemistry. Green is the most common color simply because our atmosphere has highly concentrated oxygen between 100 and 300 kilometers up. Blue and purple occur lower down, where nitrogen is abundant. But look at the red aurora. It's super rare and only happens at extreme altitudes above 300 kilometers. Why? Because of something called collisional quenching. At lower altitudes, oxygen atoms bump into each other and lose their energy way before they have the time to emit a red photon. So only in the ultra-thin air at the very edge of space can those rare red auroras actually form.
Just as the colors tell us about chemistry, the shapes tell us about physics. You're generally going to see 2 types. Discrete auroras are those sharp, distinct, readable curtains and rays of light. These are caused by electrons being directly accelerated by powerful electric fields along our magnetic field lines. On the flip side, you have diffuse auroras. These look like hazy, sometimes pulsating patches of light. They don't have those sharp structures because they're produced by electrons that have been broadly scattered by complex plasma waves, rather than a direct, localized acceleration.
Let's pivot to part 4, the space weather threat. So those spectacular colors we just talked about, they are actually giant neon warning signs of invisible electromagnetic storms raging right above us. The aurora is beautiful for sure, but it also means our planet's magnetic shield is currently absorbing a violent cosmic impact. To monitor this very real threat, scientists use the CAP index. It's a planetary scale from 0 to 9 that measures geomagnetic activity. Anything hitting a K5 or above is officially classified as a geomagnetic storm. Now, to give operators of sensitive infrastructure advance warning, we rely on satellites like DCOVR, which is parked a million miles away between Earth and the Sun. DCOVR basically sniffs the solar wind, giving us a crucial 15 to 60-minute heads up before the brunt of a solar storm smashes into our magnetosphere.
And history shows us exactly why we need those warnings. In 1989, a storm collapsed the entire power grid of Quebec in seconds, literally leaving millions in the dark. In 2003, the Halloween storms caused blackouts in Sweden and actually damaged transformers down in South Africa. In May 2025, an extreme G5 storm lit up the skies as far south as Florida and Spain, and incredible auroras were even seen across Australia in late 2025. As we march forward in time, our reliance on delicate electronics and satellites is just skyrocketing, which means our vulnerability to these expanding auroral zones is higher than it's ever been. So, the crucial point is, this isn't just a hypothetical, theoretical threat. It hits our wallets directly. During that extreme G5 storm in May 2024, the changes in the ionosphere severely delayed GPS signals. Now, for average people, maybe Google Maps was a little glitchy, but for American farmers using precision agriculture tech, like those massive tractors that rely on pinpoint GPS to plant seeds at exactly the right time, the system just failed. In just a few days of downtime, those GPS propagation delays cost American farmers an estimated $500 million in potential profit.
Which leads us to a truly terrifying question. What if a Carrington event happened today? Back in 1859, the Carrington event was so powerful that auroras were seen near the equator. Telegraph systems actually caught fire because of the electricity surging through the wires. If a storm of that exact magnitude struck our highly interconnected, modern digital infrastructure today, we wouldn't just be looking at a few broken tractors. We'd be looking at a global catastrophe with consequences stretching into the trillions of dollars.
In a modern superstorm, the casualties would be severe. The fluctuating magnetic fields induce massive electrical currents in the ground. These travel up into our power lines and can literally melt large, multi-ton power transformers. High-frequency radio communications would completely black out. The upper atmosphere would heat up and expand, creating drag that could literally pull low Earth orbit satellites out of the sky. Global aviation would be thrown into chaos as polar routes are abandoned to avoid radiation and loss of communication. The aurora is beautiful, yes, but the storm that drives it is utterly ruthless.
Finally, Part 5, Beyond Our Home Planet.
So, it turns out Earth isn't the only rock out there with a spectacular light show. If we zoom out, we see that the physics of the aurora apply all across the cosmos, but with some absolutely wild variations depending on the local environment. Just look at the difference between Earth and Jupiter. Earth's aurora is driven by the solar wind and glows in visible light that our eyes can actually see. Jupiter, on the other hand, has a magnetic field 20,000 times stronger than ours. And while it does interact with the solar wind, Jupiter's massively powerful auroras are uniquely fueled by its own moon, Io. Io is highly volcanic and is constantly erupting sulfur dioxide into space. That sulfur becomes ionized plasma, gets caught in Jupiter's massive magnetic field, and powers permanent roaring auroras. But here's the kicker. They're entirely invisible to human eyes, only showing up in X-ray and ultraviolet wavelengths.
Right now, we're riding the wave of solar cycle 25, which has dramatically outperformed early predictions, peaking in activity right now and continuing into 2026. We are literally living through some of the most active space weather in 2 decades. The aurora reminds us that we are completely tethered to our local star, cocooned within a magnetic shield that takes a daily beating just to keep us safe. So, as you look up at the next breathtaking display of the northern or southern lights, appreciating its ancient beauty and its complex chemistry, it's really worth asking, as our world becomes ever more reliant on fragile technology, are we truly ready for the next great celestial storm? Thanks for joining me on this explainer, and keep your eyes on the skies.